Right now, as you hear this, our well-behaved sky is glitching. In a single September week, near-Earth asteroids buzzed past in tight sequence, the green comet sharpened into view, and a brand new interstellar stranger called 3I Atlas slid toward the Sunday. Space is supposed to be random, yet the timing feels scripted. Coincidence, or the first page of a larger pattern? We will investigate together, fast, clear, no hype. I will show what happened, why it matters, and what comes next. Join the hunt. Like and subscribe so you do not miss the next window. Here is the paradox that pulled astronomers out into the cold at midnight. Mid-September of 2025 was forecast to be quiet, routine sky traffic, data logged and filed. Instead, the week unfolded like a meteorologist's map suddenly filling with severe storm icons. A mountain-sized rock, the near-Earth asteroid designated FA22, swept past at a distance a little over twice the gap from Earth to the Moon, about 835,000 kilometers. It was large enough to dominate headlines, yet it did not travel alone. Smaller objects were already threading by. One of them, RJ2, slipped inside a single lunar distance only 3 days earlier. On paper, none of this breaks the rules. In the gut, the timing felt rehearsed. Then the sky added another act. Near the constellation Virgo, a comet discovered by the SWAN instrument began to glow for backyard observers. At dusk, photographs showed a faint green brushstroke hanging near Mars. Comets are fickle, fragile, and often brief, but this one brightened on cue as though keeping time with the asteroid parade. And while everyone tilted up to watch, a very different body took its place on the horizon of the possible. 3I Atlas, only the third confirmed interstellar visitor in human history, was accelerating toward perihelion, the moment of closest approach to the Sun, before disappearing into glare and reappearing in early December for the best scientific look we may get for years. If this week feels arranged, that is because our brains are wired to notice patterns and write stories around them. That wiring is ancient and useful. It also makes us vulnerable to charming coincidences, so we will do what good investigations always do. We will put the drama on a leash and let the facts run. First, the facts of the clustering. FA22 is between 1 and 300 meters across. At typical near-Earth speeds, around 10 to 11 kilometers per second, its kinetic energy would translate into tens of millions of tons of chemical explosive if it were to hit. It did not. RJ2 did not. A dozen more sub-lunar passers also did not, yet each safe miss is a message. You do not learn to read the weather by ignoring close calls. Second, the comet. SWAN finds these icy bodies by watching for hydrogen released as water vapor breaks apart in sunlight. That means a discovery often arrives with a built-in chemistry lesson. A green tint in the coma is a classic hint of gas excited by the Sunday. As comets fall inward, pressure builds inside, surface crusts crack, and jets open like steam vents along a frozen shoreline. Sometimes the nucleus survives the heat. Sometimes it breaks apart and leaves only a glowing trail, beauty and fragility in the same frame. Third, the interstellar visitor. The team that spotted 3I Atlas in early July treated it at first like any other moving fuzzball among the stars. Follow-up measurements changed the story. The orbit was not a closed ellipse. The path was hyperbolic, the celestial signature of an object with enough speed to escape the sun forever. That gives us 2 gifts and 1 frustration. Gift 1 is time to plan. The dates matter. Perihelion in late October, hidden by the Sunday, then a December geometry that lines up Earth, instrument, and target for a clean look at about 1.8 astronomical units. Gift 2 is chemistry. Early spectra, hinted at a carbon dioxide heavy coma and unusual metal lines, the sort of fingerprints that tell us where in a different planetary nursery this body likely formed. The frustration is glare. The best drama happens while the curtain is down. So here is how we will proceed. We will rewind the week the sky felt scripted and examine why it looked that way. We will keep the human scale front and center. What does a safe pass mean if you live 200 kilometers from a hypothetical impact? What does wave height do as it races away from an ocean strike? How does warning lead time convert fear into planning? We will step from asteroid mechanics to comet survival to interstellar chemistry, and we will separate what we can test from what we merely feel. The tone is urgent because the calendar is urgent. The pre-dawn of December is not just a pretty observing window. It is a once-in-a-decade chance to study material from another star system without launching a mission across the void. The same week in September that made the sky look busy also reminded us that our detection network works when we invest and fails when geometry hides the danger in the sun's glare. It is a hinge moment where better eyes and better judgment change outcomes, and at the center of it all is a single, modest promise. You will leave this investigation knowing exactly what happened in September, what 3i Atlas is and is not, what the risks are, where the hype begins, and how to be part of the observation culture that makes science stronger. Keep that curiosity awake, keep that skepticism sharp. The night the sky stopped behaving is the night we started paying attention. Start with a wall calendar, 7 boxes in a row. Now drop pins where rocks and ice skim past Earth. 1 pin lands on the 18th for FA22 at a bit more than twice the Earth-Moon distance. Another pin lands 3 days earlier for the tiny visitor called RJ2 at just under 1 lunar distance. Then, you find more pins tucked into the same week, smaller objects inside the Moon's orbit, others a little farther out. On a refrigerator door, this looks like choreography. Your brain whispers that someone set the tempo. There is a reason it feels that way. We are pattern hunters by design. If a predator moved through tall grass in a rhythm, your ancestors who noticed the rhythm lived. That instinct never left. It is useful in science too. It pushes us to test whether a pattern is real. Sometimes the sky is just rolling dice and we caught a run. Sometimes the run reveals a rule we missed. To sort those possibilities, you and I need to understand how modern sky watching actually works. Global surveys patrol the night with wide eyes. Robotic telescopes scan patch by patch and stitch the sky like a quilt. Each patch becomes a stack of images taken minutes apart. Software hunts for dots that shift against the background of fixed stars. The system flags a mover. Observers at other sites take more images, so the motion is not a fluke. A provisional track becomes an orbit. Numbers turn into a path and a speed, and a closest approach. The whole relay can happen in a single night if the weather is kind and the object is bright. When it is not, the relay takes days. Cadence is the quiet boss in this story. Cadence is how often you revisit the same patch of sky. If you check a road once a month, traffic looks light. If you park a camera there and watch all day, the highway comes alive. Rubin-class surveys promise to revisit the whole visible sky every few nights. Pair that with networks like Atlas and Pan-STARRS and Catalina, and you get a jump in discovery rate. It will feel as if new objects appeared out of nowhere. Most of them were always there. We finally looked often enough to meet them. Now add media timing. One alert will prime your attention for the next alert. The second feels connected to the first, even if the orbits disagree in every important way. That is not dishonesty. That is the psychology of news. It stacks stories by proximity and time. Our minds turn that stack into a chain. During the September week, the chain was long. A near-Earth asteroid with a headline-friendly size. Another visitor so close it slipped inside the Moon's distance. A handful of even smaller pebbles shooting the gap. A comet bright enough for people to photograph beside Mars. A confirmed interstellar traveler sliding toward the Sunday stack. Those in a row, and the sky feels scripted. The math says otherwise, yet not in a way that ruins wonder. In a random process, close events tend to clump. Statisticians call this the law of small numbers. Roll a die 30 times and you will see streaks that look uncanny. Bus arrivals feel bunched when you stand at a stop, even when the schedule is neutral. The same intuition trap lives in the sky. When an object is discovered, a small window of extra observing tends to sweep up a few more. The clump is real in your notebook even, if space is indifferent. There is also an Earth-centered bias that sneaks in. Our telescopes see best at certain angles away from the Sunday. We sleep through parts of the night. Weather erases whole continents for a week. The world's cameras are not evenly spaced and they are not all running at the same sensitivity. That means opportunities to find small bodies arrive in bursts when geometry and weather cooperate across many sites. Bursts in discovery are not always bursts in reality. They are bursts in access. Here is the key check that keeps us honest. If clustering were driven by a single cause in space, you would see it echoed in the orbits. The lines on a solar system map would point the same way. Inclinations and eccentricities would rhyme. That is not what the September logs show. FA22 has a typical near-Earth path. RJ2 is on a different track. The other sublunar passes cover a scatter of directions as you would expect from a population that was stirred by ancient gravity over millions of years. 1 week of rendezvous in our neighborhood does not mean one shepherd set the meeting. So, what are we left with? We are left with a sky that is busy in every month, a survey network that is finally fast enough to highlight the busyness, and a human story engine that loves to connect dots. The feeling that someone arranged the week is a feature to harness, not a bug to fight. It keeps you watching when the next alert goes out. It keeps scientists ruthless about bias checks. Wonder brings you in. Method keeps you here. This is why we slow down and map the timeline before we chase causes. First you list the pins, then you test the temptation to tie them with one string. Most strings will snap under scrutiny, the few that do not become physics. In this series we will keep that rhythm. High curiosity, hard breaks. The week looked scripted because our awareness expanded all at once and our attention stacked events that were in fact independent. The only author is gravity and probability, and they do not take requests. Meet the rock that made the week feel unreal. FA22 is not a world destroyer. It is not a pebble either. Put a city skyline on its side, and you are in the right scale. Researchers bracket its size between roughly 130 and 290 meters across. That is enough mass to carry a staggering punch if it ever intersected our day. It did not. On the 18th of September, it slid past at a little over 2 lunar distances, about 835,000 kilometers. In space terms, that is a friendly handshake. In human terms, it is close enough to get your attention. Close approaches are X-rays for our detection system. Every parameter we measure on a miss builds confidence for when the stakes are not academic. We track its position against background stars, time the motion with sub-second precision, and pour those measurements into orbit solvers that spit out a path and an error bar. Early numbers are wide. Each night narrows the uncertainty. You can feel the math tighten as observatories around the world tag in, pass the baton, and fill the arc with data points. The process looks calm from the outside. Inside the pipeline, it is a sprint, because a few hours of cloud or daylight can inflate uncertainty again. What makes FA22 a useful teacher is not only its size, it is the speed and angle of approach. Typical near-Earth objects move at around 10 to 11 kilometers per second relative to Earth. That velocity sets the stage for everything that follows if an object were to hit. At that speed, the air ahead of a body compresses into plasma. A stony mass this large would begin to glow high above the ground and then face a brutal decision made by physics alone. Hold together and punch through. Break apart in the air, shatter into fragments that each play out smaller versions of the same script. Numbers help, but images stick. Picture yourself standing 200 kilometers from an imaginary FA22 strike on open land. The flash could be brighter than the sun, even through haze. The shock front would arrive as a pressure wave strong enough to shatter windows across a wide region. Move closer, and you begin to enter zones where structures fail and flying glass turns injuries serious. The line between a frightening day and a catastrophic one depends on composition, entry angle, and whether the event ends in the sky or on the ground. City planners think in circles on maps. Scientists think in probabilities. Both are trying to turn chaos into preparation. The ocean version is different and demands humility. 70% of Earth is water. That means most random strikes will hit water first. When a large object dumps energy into deep ocean, it excavates a cavity that collapses and launches waves. Those waves start tall and decay with distance. Coastal shape and seabed topography decide how that energy piles up at Fecteblast, shore. A 10-meter arrival at a harbour mouth can be a few meters, a short sail away, and it can be taller a few bays along. This is why simulations matter. This is also why we refuse to pretend that one diagram covers every coastline. The kindest path is an airburst that ends high. Tunguska, in 1908, flattened forest across thousands of square kilometers without a crater. Chelyabinsk in 2013 injured thousands mostly through glass when a smaller body exploded over a city after sunrise. FA22 sits in a class that can do much more than broken windows, yet far less than global climate change. Regional disaster, not civilization ender. That distinction does not comfort a coastal mayor, but it helps a nation plan. So what did the actual pass of FA22 give us besides a headline? It gave us calibration. Radar pings refine size and spin when geometry allows. Photometry hints at surface reflectivity and perhaps composition class. Small changes in the light curve can point to tumbling. Follow up nights, lock in the orbit, and remove it from risk lists when confidence crosses a threshold. That entering and exiting of risk boards is not a tease. It is how the system is supposed to work. Early caution, rapid refinement, clear communication when the line moves. It also gave us a rehearsal for something the public rarely sees: coordination. A single observatory can discover. It takes a network to characterize. When a target is accessible to different longitudes, the baton never sleeps. Southern sites hand to northern sites. Big mirrors collect spectra, while smaller scopes track position. Amateurs with good gear sometimes fill in gaps when weather blinds the giants. The choreography is not glamorous, it is essential. Each pass like this trains the team for the night when time is short and choices carry real consequences. There is a quieter lesson tucked inside the numbers. Warning time is a multiplier on every good option. A gentle nudge, applied years ahead, can change a future miss into a wider miss with minimal drama. Wait until the object is close, and the push required grows from a tap to a shove to a desperate gamble. That is why a safe flyby like FA-22 is not a shrug. It is a reason to double down on cadence, coverage, and the sober craft of orbit determination. You protect a city long before a rock appears in the morning sky. Stand back and look again. A mountain mist, no alarms, no sirens, just a clean arc through space and a line of numbers that fit. Yet inside that quiet pass are the blueprints for how we will one day take a similar object and make sure it misses on purpose. That is the value of the near miss. It does not only reassure, it instructs. Run the counterfactual. Same object, same approach speed, near 10 to 11 kilometers per second. Same entry from space into air that thickens by the second. Only one change. FA-22 does not miss. What happens next depends on three big levers that physics pulls without asking anyone's permission: composition, entry angle, structural strength. Those levers decide whether the event ends high in the atmosphere, punches into the ground, or drops into the ocean and turns water into moving walls. Start with the airburst. A stony body in the FA-22 class is likely to break under aerodynamic stress before it can strike the surface. As it dives, the air ahead of it compresses and heats into plasma. The skin of the rock glows. Internal cracks open. The object fails violently between roughly 5 and 15 kilometers above the ground. To anyone below, the first thing is light, a flash that can rival the sun even through haze. The thermal pulse lasts seconds, long enough to scorch dry brush and ignite patches of roof tar. Then the sound arrives, a pressure wave that slams through windows across a region the size of a small country. At closer ranges, the overpressure does more than break glass. It pushes in walls, throws debris, and rattles steel. Tunguska is the reference point that refuses to fade. A few tens of meters in size, forests flattened across thousands of square kilometers, no crater. Chelyabinsk is the urban version that lives in dashcam memory. A dawn sky, a rising trail, a sudden glare, then a boom strong enough to send glass into classrooms and offices. FA-22 sits far above both in energy. Estimates near 100 megatons of chemical explosive equivalent when you fold in typical speeds. Not a global killer. Absolutely a regional catastrophe if the burst happened over a city. Now imagine the object hangs together. Denser material, steeper angle, better luck for the rock and worse for the ground. The impactor punches through the final kilometers of air and transfers its energy directly into the surface. The result is a crater on the order of a few kilometers across, with rims that rise like a frozen wave. A rough guide for a 200-meter iron body at 10. A kilometers per second lands you near a 3-kilometer wide hole and perhaps half a kilometer deep. Everything inside a large radius vaporizes or becomes ejecta. Millions of tons of rock launch outward, arc and fall as a storm of stones that keeps landing long after the first blast fades. The ground rolls with a quake in the mid-sixes on the magnitude scale. Buildings without modern reinforcement fail. Landslides and bridge damage ripple outward along valleys and slopes. The crater scenario also carries a heat story that maps onto streets. A fireball expands above the surface and then rises. Close in, anything that can burn will burn. Farther out, radiant heating chars facing walls and ignites roof edges and fields. Fire services face a patchwork of ignition points with roads blocked by rubble and glass. This is why emergency managers stare at circles on maps and run drills where the details are mundane and life-saving. Who has the foam? Who has the generators? Which hospital kept its windows from becoming knives? Shift the strike into deep water, and the physics writes a different chapter. The impact excavates a cavity in the ocean. That cavity collapses. A train of waves runs outward. The initial crest near the source can tower. Height falls with distance in a way that math can predict when the bathymetry is known. Yet coasts are not blackboards. A 10-meter wave that weakens over open water can re-amplify when it meets a continental shelf that shoals steeply, or a bay that funnels energy into a narrow throat. Travel times are fast enough to erase complacency and slow enough to demand communication discipline. Hours to cross basins, minutes to move from outer buoy to inner harbour. The same strike can be mild in one port and severe 2 peninsulas away. Because 7/10 of Earth is ocean, the water scenario is the most likely end for a random arrival. That does not mean inland cities relax. Maritime infrastructure sits at sea level by definition. Power, plants, refineries, data cables, and warehouses cluster along flat water. Waves do not read zoning maps. They ride shipping lanes and river mouths into places that have only practiced for storms that build over days, not impacts that write a coast-wide story in an afternoon. There is a tempting instinct to collapse all this into a single number. Tell me how bad on a scale from 1 to 10. Physics refuses the summary. Outcomes hinge on entry speed, density, angle, and where the target happens to be. Double the diameter and energy goes up roughly by the cube if speed holds, because mass scales with volume. Increased speed and energy climbs with the square. This is why a body we can hardly visualize can move a world we know intimately. It is also why small differences in warning time map to large differences in what is possible. Here is the lever that the human side of the story does control: lead time. If you find a threat years out, the deflection menu is rich. A small spacecraft, nudge delivered early, translates into a large missed distance later. Wait until discovery happens late, and you are left with hard choices and narrow margins. Every safe pass, like FA-22, is therefore a rehearsal for a day we would prefer never to see. We learn the geometry of entry. We rehearse communications that do not break trust. We practice being precise without panic. So yes, if it hit, 3 versions of trouble are on the table. A high flash that turns windows into hazards, a crater, and a rock storm that redraws local maps. A wall of water that races a clock and a coastline. None of those futures arrived in September. All of them live inside the same physics that moves every near miss past our door. When we understand those rules, fear turns into planning, and planning turns into options. Stand on a beach at noon and try to spot a candle flame, a few degrees from the Sunday. That is what ground telescopes face along the sunward corridor. The air glows. Scattered light washes across the detectors. The signal from a small, dark object fades into a bright smear. We are good at night. We are clumsy in daylight. Many near-Earth approach vectors thread that daylight zone. The result is a blind side that hides some of the very objects we most need to see. Geometry writes the rules. Telescopes prefer targets far from the sun in the sky. That angle has a name called solar elongation. Large elongation means dark background and long exposures. Small elongation means twilight or blue daylight and a flood of scattered light. At small elongation, even big observatories become nearly deaf to faint movers. Add weather and the Earth's rotation, and you get holes in the safety net you can set your watch by. Every 24 hours, the dayside goes blind again. There is also a phase problem. When an asteroid sits between Earth and the Sun, it shows us its night side, like a new moon for rocks. The illuminated crescent points away. Reflective brightness drops just when the sky is brightest. That double penalty pushes warning times down from weeks to days to hours. Chelyabinsk rode in on that corridor in 2013. Small, fast, sunward. No ground telescope saw it first because optics cannot stare into glare without drowning. The first detector was a blue sky over a Russian city and 1,000 car cameras. You can feel how warning time changes options. Discover an object on the night side, well separated from the sun, and follow up is easy. Track it over several evenings. Narrow the orbit. Decide whether it is harmless. If not, Years of warning open doors. A small kinetic nudge delivered far out along its path can shift the mist distance by thousands of kilometers at Earth. That is elegant, cheap, and proven in principle. Discover an object on the day side and the menu shrinks. The numbers arrive late, the error bars grow, and the conversation turns from precision to luck. Glare is not the only villain. The atmosphere itself fights you. Molecules and aerosols scatter sunlight in every direction. That is why the sky is blue. It is also why cameras fill with background noise near the sun, even at dusk. Astronomers use careful baffles and filters and timing to claw back a little sensitivity in twilight. The gains are real, but they are crumbs compared with the quiet darkness of midnight at high altitude. From the ground, twilight surveys nibble at the edge of the blind spot. They do not close it. What about pointing at the sun with instruments designed to stare at it? Coronagraphs block the disk to watch solar storms and catch sun-grazing comets. They are great for icy bodies that vent gas and create big, bright comae. They are almost useless for small, dark asteroids that reflect little light and present tiny silhouettes against a white background. Different tools for different jobs. The job of finding dark rocks near the sun wants a vantage point where the sun is behind you and the target glows for a different reason. That reason is heat. Even a charcoal dark asteroid radiates infrared light because it is warm. Space-based infrared telescopes see that glow against the cold of space. They measure size more directly than reflected light can. They do not care whether the surface is dark or shiny. Put an infrared sentry in an orbit that trails Earth, and it looks back toward the inner system at angles our ground telescopes cannot reach. The blind side begins to fade. The corridor that hid Chelyabinsk turns into a monitored lane. Until that system is fully online, we do the next best thing. We widen cadence at night to catch more objects earlier on their inbound leg. We coordinate networks so that longitude handoffs reduce gaps. We tune software for twilight hunts to push a little deeper when the sky is still bright. We practice communications that admit uncertainty early and speak plainly as numbers sharpen. The goal is not perfect certainty months ahead every time. The goal is pushing discoveries out of the dangerous last-minute zone and into the days and weeks where choices exist. It helps to think like a pilot flying with one instrument dark. You fly differently. You rely more on the gauges that still work. You change routes to keep big risks out of your path. Ground surveys are those working gauges. Infrared sentries are the missing instrument we are installing. When both sets sing, the map of threats gets cleaner. The difference between a headline and a footnote can be the simple fact that we saw the object on the night side instead of in the glare. So, the blind side of the sun is not a myth. It is a measurable gap baked into optics, atmosphere, and geometry. It explains why some objects seem to appear from nowhere, and why the safest sky is the one we watch from more than one angle. We cannot turn off the Sunday. We can change where we look from and how often we look. That is the turn from vulnerability to agency. Physics sets the rules. Engineering changes how well we play. Look west after sunset, and you understand why people once feared comets. A soft green smear near Mars, a faint tail bending away from the sun as if the sky itself were exhaling. That was the September surprise from a small traveller catalogued by the SWAN instrument. SWAN rides on a solar observatory and watches the whole sky for hydrogen glow. When a comet starts venting water, sunlight breaks the water into hydrogen that shines. SWAN notices that shine long before most backyard cameras do. A data point becomes a path. A path becomes an invitation to step outside. Comets are time capsules wrapped in frost and dust. They formed far from heat in the outer dark where grains stuck together and grew. They carry water, carbon dioxide, and more fragile molecules that do not survive near stars for long. When one falls inward, the rules change. Sunlight warms the outer layers. Ice goes straight into gas. Pressure builds beneath dust that has been welded together by cold. At first, the gas seeps through pores, then vents open, jets fire. Dust rides the gas and spreads into a luminous coma that looks like a foggy sphere around a tiny nucleus you cannot see. That green tint is not magic. It is chemistry. When sunlight hits certain carbon molecules that were hiding in the ice and dust, they glow green before the energy bleeds away. You can think of the coma as a lantern shade around a filament that you never glimpse directly. The tail is 2 stories braided together. One is dust pushed gently by sunlight into a curved ribbon. The other is gas picked up by the solar wind and stretched into a straighter, bluer streamer. On long exposures, the two can separate like strands of hair in a breeze. The word fragile matters here. Comets have strength the way a snowbank has strength, enough to hold a shape when conditions are kind, quick to rearrange when the sun begins to cook. Some survive a first dive inward, darken, and return on long loops for many passes. Others come in, fresh from the deep cold, light up like a match, then tear themselves apart and fade. The difference can hinge on spin, cracks, and how quickly new vents open. A comet that brightens steadily one week can stall or crumble the next. The same physics that makes them beautiful also makes them unpredictable. This is why SWAN discoveries feel like live theatre. The instrument does not chase comets on purpose. It maps hydrogen near the sun to study the solar wind. Yet whenever a new inward-bound nucleus begins spouting water, that hydrogen becomes a beacon. Ground observers pick up the chase. Reports roll in from farm fields and rooftops. Near Virgo, near Mars at dusk. Greenish coma, tail length growing. Brightness brushing the edge of what a patient eye can catch without binoculars under truly dark skies. It is a shared hunt, and the cast never stands still. Underneath the postcards is a stream of practical knowledge. Outgassing is a rocket engine that the comet cannot shut off. Each jet pushes on the nucleus a little. These tiny kicks add up and gently alter the path. Orbital predictions for brand new comets, therefore, carry extra uncertainty. Observers track brightness night after night to watch for outbursts and to feed models that guess whether the nucleus is holding together. If the brightening follows a smooth curve, survival odds rise. If it surges and slumps, the crust may be cracking in new places, which is thrilling and dangerous for a comet all at once. If you are holding binoculars and a phone app, the trick is to start early in twilight and know exactly where to look. The green fuzz will not jump out like a street lamp. It is a whisper, not a shout. Shield your eyes from porch lights and let them dark adapt. Sweep slowly. Look a little to the side of where you think it is, not straight on. That off-center trick taps the more sensitive part of your night vision. Take a few photographs with a tripod and a long exposure and the coma will bloom on the screen, even when your eyes barely registered it. The most honest thing we can say about a comet in this state is that it is a cliffhanger. The nucleus could fragment tomorrow. It could hold together and gift the hemisphere a prettier tale. It might even surprise everyone with a sudden flare when a patch of fresh ice vents all at once. People love to ask whether a given comet will become a classic. The universe loves to answer with maybe. That maybe is not a flaw. It is the source of the thrill. We are catching a frozen relic in the very act of waking up. So, the green brushstroke near Mars is not a threat. It is a living lab for how ice and dust behave when a deep freeze meets a star. It teaches why tails point away from the sun, why they kink and split, and why comets that survive their first plunge look different on later trips. Every frame taken by amateurs, and every spectrum taken by big telescopes add colour to that lesson. And while it glows in the western dusk, it keeps us tuned to the broader story. September set in motion, rocks raced by, a comet flared, an interstellar visitor drew near. The sky is busy, the details matter. Mark a night on your calendar 5 springs from now, April 13 of 2029. A 400-meter asteroid named Apophis will slide inside the belt of our geostationary satellites and streak across the sky fast enough for you to see it move with your naked eyes from city sidewalks and farm fields alike. That sentence sounds like a movie trailer. It is better than a movie because the risk is zero. The orbit is solved to high confidence. The spectacle is real. The lesson is larger than the rock. Apophis has been on our radar for decades. In its early years, it spooked risk lists when the first sparse data allowed a tiny chance of impact. Then radar and optical follow-ups crushed those odds to nothing. That journey from maybe to no is how planetary defense should feel. Caution first, then patience, then measurements that cause the probability to collapse. What remains is a natural experiment on a grand stage. Think of Earth as a heavy hand passing near a gravel heap in slow motion. Tides pull on Apophis from head to tail as it races by. The stretch is not enough to tear it apart. It is enough to shuffle grains and pebbles across the surface and to tweak the spin. A patch that was sloped gently might slump. Boulders can shift a few centimeters and leave fresh scars. Fines can flow downhill like dry snow into hollows. The asteroid that arrives will not be identical to the asteroid that leaves. Speed will make it feel alive. 50,000 kilometers per hour, written as a number, is hard to feel. Stand under a dark sky, and you will not need the number. You will see motion against the stars in real time. Astronomy usually teaches patience. This is the opposite. A bright dot crosses a field of view like a bead on a wire. City dwellers who have never watched a meteor shower will look up and point. Teachers will plan field nights that start on time for once. We will not watch with eyes only. A repurposed spacecraft called OSIRIS-APEX is on a trajectory to meet Apophis after the flyby. That craft carries heritage from a mission that grabbed a sample from another near-Earth asteroid and returned it to the Utah desert. Now it becomes a forensic team. It will map the surface after the tidal stress test. It will measure rotation with exquisite care. It will look for landslides and for places where the regolith has been freshly turned. These maps will become templates for how gravity reshapes small bodies during close planetary encounters. Why does that matter for anything beyond curiosity? Because deflection strategies and resource plans both depend on how rubble piles behave when pushed. A kinetic impactor like the DART mission delivers a punch. The surface and subsurface structure decide how much of that punch becomes a change in momentum and how much becomes a plume of debris with less effect. Tidal reshaping is a natural analog. Earth will be the invisible hand that does the pushing while we take notes. Those notes feed models that one day may guide a mission to save a city. There is public risk to manage on the communication side too. A bright, moving object near satellites will set imaginations on fire. The right story is simple and true. This is the closest pass by a large asteroid in recorded human history, and it is harmless. You can go outside and enjoy it. You can take your child or your grandparents and let them watch a rock a quarter-mile wide. Change the way they feel about space. Nothing bad will happen because the geometry forbids it. The best part of a safe spectacle is what it teaches for free. We can practice the choreography of global observation without the pressure of a countdown. Radar teams can schedule long tracks. Photometry groups can coordinate continuous coverage across continents as day becomes night and back again. Amateur observers can test calibration routines on a target bright enough for modest gear. Newsrooms can rehearse headlines that inform without over-promising. All of that rehearsal will echo into nights when the stakes are not zero. Apophis also offers a cultural reset. For years, asteroid stories arrive framed as worry or as punchlines. This one is awe and method in a single package. You will be able to see a minor planet move with your naked eyes and then tap your phone to see a spacecraft dive in for the close-up days later. The loop from look up to look down to look inside will be tight enough to hold in memory. That loop is how you build a generation that trusts measurement more than rumor. So keep April 13 of 2029 warm in your mind. The flyer is not a threat, it is a teacher. It carries the lesson that orbits can be solved, that tides can write on stone, and that a world can use a harmless close pass to prepare for a harmful one decades from now. The closest big flyby is billboard for a simple idea. Good sky watching turns fear into fluency. Picture an ordinary survey night in early July. Automated telescopes comb the southern sky from Chile, snapping quick exposures and comparing them with exposures taken minutes before. One faint dot shifts its position more than background stars allow. Software flags the mover. Humans check the pixels and schedule follow-up. The first assumption is boring in the best way. Probably a local comet or a near-Earth asteroid wearing a fuzzy halo. Then the math tightens. The orbit refuses to close. Fit after fit says the same thing. The path is not an ellipse that returns. It is a hyperbola that escapes. The dot is not from here. That is how 3i Atlas joins a very short guest list. In the modern record, we have seen only 2 confirmed interstellar visitors before this one. In 2017, a strange tumbling object called Oumuamua slid through without a visible coma and left arguments in its wake. In 2019, a classic comet named Borisov arrived looking exactly like a comet and reassured the cautious that nature could deliver wanderers from other suns. Now comes 3i Atlas with the timing of a performer who knows the stage. Perihelion, near the end of October, hidden by glare. A December reappearance in the pre-dawn sky when Earth, Sun and orbit place it at about 1.8 astronomical units from us. Far enough to be harmless, close enough to be rich with data. Unbound paths feel romantic until you translate them into physics. A hyperbola means the visitor carries more velocity than the sun can leash. Imagine dropping a pebble into a deep well so fast that gravity cannot turn it around. That is the essence of escape. Three-Eye Atlas fell toward the sun, curved as all bodies must, and will leave forever on the far side. We will not get a second pass. That single fact upgrades every minute of our observing window into something like a once-only field trip to another planetary system. What does it bring with it? Early spectra suggest a coma in which carbon dioxide dominates more than usual, while water seems relatively muted. That ratio rings bells for anyone who studies where ices condense in a newborn system. Water freezes closer to a star than carbon dioxide does. If carbon dioxide stands out, perhaps the nucleus formed farther from its parent star, in deeper cold, where water was scarce or shielded. Another clue sits in the metal lines. Nickel shows up strongly, while iron looks weak. In our backyard, iron and nickel usually travel as a matched pair. Their mismatch here hints at either unusual birth chemistry or long years of processing by cosmic rays in interstellar space. None of that requires anything supernatural. All of it is profoundly alien in the best scientific sense, non-local, informative, testable. Even the shape of the light around it has stories to tell. As sunlight wakes buried ices, jets of gas open and push dust into a coma that grows and a tail that points away from the sunday. Multiple tails with slightly different directions can appear as different gases, and different grain sizes respond to light and solar wind. If the nucleus is rotating in a complex way, vents will swing like lawn sprinklers and create repeating patterns in brightness. If the surface carries an insulating crust, pressure can build until a seam pops and brightness jumps. Those jumps are not just pretty. They perturb the path slightly, which is why orbit predictions for active comets always carry caveats that shrink as more nights stack up. The instruments ready for this window are better than anything available when Oumuamua waved and vanished. Ground-based giants like the Very Large Telescope and Gemini can spread the light into spectra that mark molecules by their fingerprints. Space telescopes can watch in infrared where warm dust glows, a view that cares less about whether the dust is dark or shiny. If schedules hold, the James Webb Space Telescope can aim its spectrographs and pull out ratios that let chemists argue with data instead of metaphors. Narrow-band imaging can isolate metal emissions. Polarimetry can estimate dust, grain, size, and structure. Each technique is another way of asking the same question. Where and how did this thing form? Three-Eye Atlas also sharpens a long-running argument about weirdness. When Oumuamua showed non-gravitational acceleration without a visible coma, imaginations ran ahead of measurements. With Three-Eye Atlas, the behavior looks comfortably comety, while the chemistry looks startling. That is a scientist's dream. Familiar physics wrapped around strange ingredients. You do not need directed motion or radio beacons to feel wonder. All you need is a sample that records conditions we cannot build in a lab and a clock that tells you the sample might be older than Earth itself. The calendar keeps the tension honest. We lose the object to solar glare right when heating peaks. Important changes may happen while we cannot watch. Then orbital geometry hands it back in early December, and the chorus of telescopes picks up the song. First, the wide-field images to fix position. Then the deep spectra as dawn air steadies and long integrations become possible. Nights will be short, weather will be rude, teams will squeeze every hour. A clean sequence across wavelengths will let us compare lines and continua and chase any transient outbursts that signal fresh vents opening. It is worth pausing on the phrase harmless but important. In mid-December, the distance of roughly 270 million kilometers means no threat. The only danger is the one every researcher feels when a unique target is in reach and a cloud bank rolls in. That is why coordination matters as much as aperture. Southern and northern sites will trade the baton. Amateurs will monitor brightness in between professional blocks. Alert channels will pass along any jump so that spectrographs can pivot before the signal cools. Three-Eye Atlas is not a riddle from nowhere. It is a messenger from somewhere quite specific, even if we never find the address. Its orbit tells us it came from beyond the sun's reach. Its chemistry whispers that it froze in a nursery unlike ours, perhaps in deeper cold with a different recipe of ices and dust. Its activity will sketch vents and crusts and rotation in ways we can compare with homegrown comets. If all goes well, December will turn a faint greenish smear into a dataset thick enough to argue about for years. That is how you learn a galaxy. One passing grain at a time, read carefully under a quiet sky. Open the spectrum and the story changes tone. Light from Three-Eye Atlas is not just brightness. It is a barcode of chemistry, etched into the glow around the nucleus. When telescopes spread that light into its colors, certain lines jump out and others hide. The early readout pointed to a coma, unusually rich in carbon dioxide with water playing a quieter role than we expect. At the same time, nickel was speaking loudly, while iron whispered. In our backyard comets, iron and nickel usually sing together. Here they do not. That mismatch is the first clue that we are dealing with a recipe written far from home. Let us translate what a carbon dioxide-heavy coma means. In a newborn planetary system, ices do not condense all at once. Water can freeze closer to the star. Carbon dioxide requires deeper cold. Think of a protoplanetary disk as a vast freezer, with shelves at different temperatures. If a body forms on the outer shelf, carbon dioxide becomes abundant, while water may be less available or buried. Transport can move materials inward and outward, but a strong carbon dioxide signal hints that the original pantry was very cold indeed. That points to a birthplace far from a parent sun, or to an unusual disk where temperatures and chemistry never matched ours. Now the metals. Nickel lines look vivid, while iron looks muted. Under typical solar system conditions, the ratio of iron to nickel in cometary gas hovers near what we see in the Sunday. Iron and nickel are forged together in stars and usually travel together in dust grains. To separate their voices, you need either a birth cloud with different elemental ratios or a long process that changes surfaces grain by grain. One candidate is cosmic ray processing over immense spans of time. High-energy particles break bonds and knock atoms free in a slow sandblasting called radiolysis and sputtering. If nickel hides in compounds that weather more slowly while iron escapes more easily, the coma would lean nickel-rich. Another candidate is thermal sorting during repeated microheating events in interstellar space, where trace warming and cooling cycles drive off some materials while leaving others behind. Both ideas are testable as better spectra arrive. Strange ratios can also grow from the way a nucleus wakes up. Imagine a multi-layer cake built in a very cold pantry. The top crust becomes dehydrated and compacted during the first breaths of sunlight. Beneath that crust, pockets of carbon dioxide-rich ice remain. When cracks open, those pockets vent first. The result is a carbon dioxide flash that outweighs water in the measured gas, even if water is still abundant deeper down. As the sun bakes longer, the water layer wakes and the ratio shifts toward normal. This temporal choreography is why repeated spectra across many nights matter as much as the first one. There is a fair challenge that belongs on the table. Could our instruments be fooling us? Lines from different molecules blend. Dust can scatter light and hide or mimic features. Telluric absorption from Earth's own air imprints patterns that must be removed with care. Good teams know these traps and design their observations to step around them. They take reference spectra. They vary slit angles. They use multiple wavelength windows that cross, check one another. When independent groups on different nights report the same carbon dioxide dominance and the same nickel emphasis, confidence rises. Skepticism is a habit, not a refusal. Chemistry is a map, and maps point to places. A carbon dioxide strong, water-modest signature points to very cold formation zones or unusual abundance patterns. A nickel loud iron soft signature points to non-solar elemental ratios or to surface processing that preferentially freeze one metal over the other. Put those clues together and a picture forms. The nucleus likely assembled far from a small, dim star or in the outermost regions of a larger system. It was then ejected during the rough teenage years of planet formation and spent eons in interstellar deep freeze, where radiation slowly tuned its surface. None of that requires exotic technology or special pleading. It requires time and a galaxy that never runs out of places to make ice and dust. Activity patterns add footnotes to the map. Multiple tails with slightly different angles tell us that more than one gas is streaming off the nucleus. Dust grains of different sizes scatter light differently, so polarization measurements can hint at grain structure and even porosity. If the rotation is slow or tumbling, vents will sweep across sunlight like lighthouse beams, modulating the flow and spiking brightness in fits and starts. Each spike is a natural experiment that exposes fresh material, briefly giving us a look at chemistry that has not been cooked by earlier outgassing. You can think of these episodes as core samples without a drill. There is also an important guardrail on the road to wonder. Alien here means non-local, not paranormal. 3I Atlas follows gravity like every other comet. Its path curves exactly as Newton and Einstein say it should. The outgassing produces tiny pushes that we can model with the same math used for homegrown comets. What makes it astonishing is not that it breaks physics, but that it stretches our catalogue of what nature can assemble in different nurseries. In that sense, the object is not an answer. It is a calibration point that widens the axis of possibilities. The most useful outcome would be a time series that tracks the carbon dioxide to water balance through and after perihelion, and a parallel series that checks whether nickel stays loud while iron stays muted. If the ratios remain extreme, birth chemistry likely dominates. If they drift toward familiar values, layered venting and seasonal exposure may be the main actors. Either way, the result is gold. A steady ratio fingerprints a distant nursery. A sliding ratio reveals structure inside the nucleus and the physics of waking up after a billion-year sleep. So the phrase chemistry that should not work is really shorthand for chemistry that does not match our local habits. 3I Atlas is teaching us that the galaxy's pantry stocks more recipes than we had tasted. If we listen carefully, through December's window, we will come away with a richer map of where this traveller came from, and a sharper sense of how many different ways there are to build a world. The lines in that spectrum are not just colours, they are coordinates. Stand under a clear pre-dawn and imagine the comet as a narrator with a hoarse whisper. Every flare in brightness is a sentence. Every kink in the tail is a pause where the voice cracks. Comets speak through sunlight and gas, and 3I Atlas has a lot to say. The nucleus is small compared with the blurry glow you see, yet it governs the entire performance. It spins, it warms unevenly. It hides ancient ices beneath a crust that acts like a stubborn lid. When the lid fails along a seam, a jet opens and the story jumps. Multiple tails are not a magic trick. They are the signatures of different materials escaping at different speeds. Dust is heavy by comet standards and slides outward along a curved path under the steady push of sunlight, like ash drifting from a campfire in a light breeze. Gas is nimble and couples to the solar wind, the stream of charged particles our star breathes into space. That flow can yank ionized gas into a straighter filament that points away from the sunday. On long exposures, the dust ribbon and the gas filament separate into distinct strands. Two pens, writing in the same sky. Rotation adds rhythm. If the nucleus spins slowly, a vent may face the sun for hours, then slip into shadow and cool. If it tumbles, vents sweep across day and night like lighthouse beams. The coma brightens, quiets, and brightens again. Photometry catches that beat by measuring total light night after night. A smooth rise can mean steady heating and a nucleus that is holding together. Sharp spikes can signal sudden exposure of fresh ice or the collapse of a crusted-over pocket. Those spikes are where the comet tells you it just tore open a new page. The crust itself deserves a closer look. Over many distant orbits, dust that fails to escape falls back and blankets the surface. Sunlight bakes this fallback layer into a compact shell. Under that shell, the ices are still volatile. Pressure builds as heat seeps inward. Gases probe for exits. At some critical point, the shell fails and a geyser of gas and grit erupts. The plume expands, sunlight catches it, and the comet glows a little brighter. That brightness drift across hours is the comet writing marginal notes to the main story of its orbit. Polarization is a big word for a simple idea. Sunlight that scatters off small grains of dust becomes organized in a way that tells you about the sizes and textures of those grains. Instruments can read that organization and infer whether the dust is fluffy like fresh snow or compact like beach sand. Fluffy grains make softer light. Compact grains make a cleaner glint. With that one tool, observers can sketch the grit the comet is shedding without ever seeing a grain up close. It is forensic science, done with starlight. There is a small, persistent push hidden in all this beauty. Every jet acts like a tiny thruster on the nucleus. The thrust is weak, but the clock runs long. Over weeks, those nudges shift the path slightly. That is why orbit predictions for active comets carry wider uncertainty at first and shrink only after the outgassing pattern stabilizes. It is also why observers crave coordinated coverage. When the light jumps, telescopes can swing to spectra quickly and catch fresh gases before they dilute. A good time series turns chaos into a readable diary. You can take this down to human scale and feel it. Think of a frozen pipe warming at dawn. The first trickles find hairline cracks. A seam opens with a pop, and water sprays. The flow changes as pressure drops. The comet is that pipe crossed with a pinwheel, spinning, cracking, venting. New jets change the balance of forces that were steady an hour earlier. The result is a living object rather than a rock on rails, and that liveliness is the point. It lets us sample layers built in a distant nursery, one outburst at a time. None of this requires drama for its own sake. The drama is already written in sunlight, ice, and vacuum. Our job is to listen well. To do that, we keep two habits alive at once: patience for the slow curves that show thermal physics at work, alertness for the sudden spikes that expose fresh material. Together, they turn a greenish blur into a coherent message about how comets are built and how they age. In the next window, when 3i Atlas clears the glare, that message will be louder. The narrator will have warmed up. The sentences will come faster. If we are ready, we will catch every word. Here is the difference between fear and fluency. Fear waits for an object to appear in a blue sky. Fluency builds tools that shift the odds long before the headlines. Over the past few years, those tools have quietly crossed a threshold. We are not just watching rocks. We are learning how to move them, how to find them earlier, and how to close the very gaps that once embarrassed us. 4 names carry the story: Double Asteroid Redirection Test, Hera, Rubin, Near Earth Object Surveyor. Together, they turn a shooting gallery into a managed traffic pattern. Start with the push. The Double Asteroid Redirection Test was a one-way spacecraft that hurled itself into a moonlet called Dimorphos to see if a small nudge could change an orbit in a measurable way. It did more than that. It shortened the moonlet's period by dozens of minutes, when a few minutes would have counted as success. The reason is, as human as a boot step in snow, the impact did not only shove the rock, it kicked up a plume that flew off into space. That plume carried momentum in the opposite direction, which amplified the push on the body that remained. Engineers call that a momentum multiplier. You can feel the idea without equations. A punch plus a spray moves more than a punch alone. The test matters because it turns the word deflection from a movie term into an engineering term. It means we can design a mission to deliver a measurable change if we have time. Time is the tyrant in all of these stories. A tiny nudge delivered years ahead translates into a large missed distance at Earth. A larger nudge delivered late may be impossible. The lesson of the impact test is therefore married to a second lesson. Find objects earlier, or the physics hands you a bill you cannot pay. That is where Hera enters. The European spacecraft is en route to the same binary system to take the careful after photographs that every forensic team craves. How deep is the crater? How porous is the surface? How much of the push became motion, and how much became dust? Hera will measure mass, map boulders, and lock down the before and after state. Those numbers fold back into models so the next mission planner can run honest scenarios. If the target is a loose rubble pile, the optimal hit looks different than if the target is a denser shard. If rotation is rapid, the timing and angle of attack may change. Hera is not a sequel. It is the lab report that makes the first experiment grow up. Finding targets earlier requires a different class of tool. The Rubin Observatory is a camera with a sky for a canvas. It will scan the entire visible dome every few nights and do it again and again with relentless cadence. Cadence is oxygen for discovery. Revisit often enough, and faint movers appear where previous surveys saw only stillness. Link a few visits, and you get a track. Link a few tracks, and you get an orbit. Rubin will flood the discovery pipeline with more small bodies than any single facility before it. That flood is not noise. It is the missing data that turns near surprises into routine finds, with weeks or months of warning. Rubin also changes how we confirm paths. With rapid revisits, you can cut uncertainty down while an object is still far away. That means you can remove a scary maybe from a risk list before rumor fills the gap. It means you can hand off the most interesting or worrying targets to bigger telescopes for spectra and radar before the geometry gets worse. In short, cadence buys clarity, and clarity buys calm. Then there is the corridor that ground telescopes cannot own. The sunward blindside that delivered Chelyabinsk will not fix itself. The Near-Earth Object Surveyor is the answer that finally matches the problem. It is a space-based infrared telescope that will fly in a position trailing Earth. From there, it will look back toward the inner solar system and see the warm glow of dark bodies against the cold of space. Reflectivity no longer matters. The the sun no longer drowns the signal. Approach vectors that were invisible from the ground become visible early enough to act. When the sentry hums, the game changes from hope to schedule. These tools only work as a team. A space-based sentry spots a warm mover coming up the sunward lane. Rubin locks its position from the night side and narrows the orbit. Radar, when the geometry allows, pings for size and spin. If the track stays unfriendly and the timeline is long enough, a kinetic mission planner reaches for playbooks refined by double asteroid redirection test and by Hera. If the track is harmless, the same instruments pivot to science, because every rock is a free geology lesson and every comet is a chemistry class you do not have to launch. There is a human layer worth stating plainly. Capability without communication can still fail. The public needs to hear early that uncertainty is normal at first and that probabilities will move. Scientists need to resist the urge to hold results until perfect, because late perfection is less valuable than early clarity that evolves. Newsrooms need honest language that avoids both hype and a shrug. The best system couples hardware to habits, telescopes to trust. The headline that matters sits behind all the brand names. We have begun to change outcomes, not with magic, not with a silver bullet, but with a chain that starts with earlier detection and ends with a gentle nudge delivered in time. That chain only holds if every link is maintained. Surveys need funding, even when the sky is quiet. Missions need green lights years before the object they will one day deflect is even discovered. If that sounds like insurance, it is. The premium is modest compared with the bill a city would pay after a late surprise. So the plan is simple and demanding. Keep building the eyes. Keep flying the sentries. Keep practicing the push while the stakes are low. The next time a mountain-sized rock writes itself into our calendar, we will not just watch it pass. If needed, we will move it. Quietly, early, on purpose. Stand at a bus stop for 20 minutes, and 3 buses arrive at once. Your brain screams conspiracy. In statistics, this is ordinary life. Random processes clump. That is the first rule to carry into the September week that felt choreographed. Rocks and ice do not consult a calendar, yet our attention does. When one close approach makes headlines, it primes your senses to notice the next one. Stacking attention turns a line of independent events into a story arc. The cure is not to silence the story. The cure is to measure it. Start with the law of small numbers. In short runs, randomness looks strange. Flip a coin 10 times and you will see streaks of heads that feel rigged even though the coin is honest. Sky surveys operate in those short runs every night. You get a handful of discoveries in a handful of hours and the streak stands out. Extend the window to months and the pattern often dissolves into background. That widening of context is one of the simplest tools we have to de-enchant a dramatic week. Now add selection effects. Telescopes do not watch all directions equally well. They avoid the Sunday. They chase clear weather. They revisit some patches more often because of schedule and science goals. Increase cadence and you increase finds. That change feels like a surge in reality when it is mostly a surge in awareness. The Rubin era will make this vivid. When the whole visible sky is scanned every few nights, discovery clumps will become common simply because the camera is relentless. A burst of pins on a calendar will be a burst of exposure, not a signal from the cosmos. There is also the human amplifier called availability. If a close approach becomes a trending topic, you will hear about the next one even if it is tiny and routine. Media adjacency is not physics, yet it shapes perception. A week with 5 small passes can feel more alarming than a quiet month that includes one larger object at a greater distance. The sequence fools us because our minds compress the timeline and exaggerate the link. So we test the link. If clustering is real in space rather than in perception, orbits should rhyme. You would see similar inclinations and long axes that line up like arrows. You would find shared velocity signatures hinting at common origin. September did not show that harmony. FA22 followed a typical near-Earth path. RJ2 came from elsewhere. The sublunar passes filled a scatter that matched the background population. That is exactly what you expect when gravity has been shuffling small bodies for eons. The sky delivered coincidence. Our brains delivered pattern. Coincidence is not an insult. It is a powerful explanation that must be ruled out before we chase exotic causes. Think about lightning. It rarely strikes the same point twice in a short span. Yet clusters do happen on stormy afternoons without any mystery beyond where the charge built up. The inner solar system is a permanent storm of potential encounters. Earth simply rotates through regions where small bodies happen to be passing at the same time. Some weeks the calendar fills, some weeks it does not. The process needs no conductor, bias. Checks keep us honest. One check is seasonal geometry. Certain months place the night side of Earth in directions where near-Earth objects are easier to catch. Another is weather correlation across observatories. When the Pacific Rim has clear skies, that arc of longitudes can report more finds than average. Neither of those effects changes reality. Both change what sits in our notebooks. Distinguishing reality from access is the quiet craft under every dramatic plot. None of this means we dismiss the uncanny sensation that many viewers felt. That sensation is the fuel that keeps us looking. The work is to harness it without letting it steer. The mantra goes like this: count first, compare orbits, check survey cadence, correct for glare and weather. Only then ask whether something deeper is at play. Most of the time, the deeper answer will be no. Occasionally, you get a yes that survives the gauntlet, and those are the days the field moves forward. Here is the balanced verdict that protects both curiosity and truth. The September cluster looked like a pattern because our capability and attention peaked at the same time. The sky did not break its rules. We simply watched more closely and stacked stories that were independent. That does not shrink the wonder. It reframes it. The marvel is that we finally have eyes sharp enough to notice the ordinary richness of a dynamic solar system. When you understand that, a busy week stops being a scare and starts being a sign that the instruments are doing their job. Let us test the tempting idea head-on. Could a few kilometre-class visitor tug a whole week of asteroids into a neat parade? Gravity is universal, yes. It is not generous. The pull between two bodies fades fast with distance. Double the gap and the pull drops to a quarter. Stretch the gap to millions of kilometres, and the numbers become whispers. The sun dominates. The planets follow. Everything else is background music. An interstellar comet like 3, I-Atlas, is a tap on the shoulder in a room where the star and the giants are already shouting. Scale helps. Picture a grain of gravel passing through a stadium while the floodlights blaze and a marching band stomps. The gravel has gravity. You could measure it with instruments that never lie. You could also stand a meter away and feel nothing. That is the relationship between a small visitor and the near-Earth population spread through the inner system. If herding were real at those ranges, you would see it in the maps. Orbits would bend in chorus. They do not. Dynamics gives us a second check. Real shepherding leaves fingerprints. Families of objects share traits. Their tilts match. Their long axes align. Their speeds carry a common accent. September's objects do not talk that way. FA22 lives on one track. RJ2 lives on another. The sublunar passers that week came from a scatter of directions that matched the background statistics of near-Earth space. Nothing points. Back to a single meeting point with 3i Atlas. Nothing hints at a shared past with a hyperbolic stranger. Timing is a third trap. The week feels tight on a calendar. In orbital time, it is a blink separated by wide lanes. Even if 3i Atlas had the mass to matter, which it does not, you would need close approaches measured in thousands of kilometers to deliver noticeable nudges. Those approaches did not happen. The visitor sat far away in geometry that placed it near the sun from Earth's perspective, while most of the asteroids crossed our sky at much larger separations. Long-distance gravity does not organize traffic. It drifts through it unnoticed. There is also a symmetry test. If a small body could herd at those distances, many comets would too. We have watched sun-grazers and bright comets for centuries and seen no repeatable choreographies of nearby asteroids tied to their paths. The rare times small bodies truly shepherd others. They do it up close in rings or along resonances, where orbits exchange energy, rhythmically, over many cycles. That is not this case. This is a one-pass visitor on a path that never closes, sliding through a system whose rhythms were set long before it arrived. The human mind wants a conductor, because conductors make stories clean. Remove the conductor, and you risk losing the plot. You do not need to. The plot that remains is better than fiction. Gravity at large scales is simple and strict. The sun rules, the planets sculpt. Small bodies move where those fields allow. Discovery bursts happen when our eyes improve, when weather cooperates, and when geometry gives us favorable angles. September was that. Nothing more mystical. Nothing less interesting. There is one place where 3i Atlas does push on its own life, and it is worth keeping separate from any herd fantasy. Outgassing acts like tiny thrusters on the nucleus. Over weeks, those jets can shift the visitor's path a touch. That self-push is real and measurable. It does not reach outward across millions of kilometers to steer unrelated objects. The effect ends at the edge of the coma and the tail. So let us retire the shepherd story with respect. It came from a good instinct to find causes. It fails the scale test, the fingerprint test, and the symmetry test. That does not empty the week of wonder. It frees us to look at the right culprits. Random clustering in a busy sky, survey cadence that turns faint movers into finds, media stacking that makes independent events feel like a chain. When we clear false causes, we can see the real machinery working without drama. That is how careful awe sounds. Imagine the Milky Way as a layered city in the dark. There is the thin, bright downtown disk where the sun lives now, full of younger stars and busy traffic. And there is an older district called the thick disk, a wide and slightly puffed layer, whose stars were born when the galaxy was rougher, poorer, in heavy elements, and more chaotic. If 3i Atlas really carries odd chemistry and an ancient look, this older district is a natural place to search for its roots. Older stars grew up with a different pantry. Heavy elements like iron and nickel were rarer and mixed in different proportions. That matters because planets and comets are built from whatever dust those stars could make. If you start with a recipe that leans one way, your frozen leftovers will lean with it. A nucleus that vents a lot of carbon dioxide while water stays modest fits a picture where the birthplace was colder and farther from its parent sun. A coma that shouts nickel while iron whispers fits a picture where the dust grains formed under non-local rules. How does a small body like this leave home? The early years of any planetary system allowed. Giant planets migrate, smaller worlds scatter like billiards. Swarms of icy fragments are flung outward by close passes with big neighbours. Most of those fragments fall back or park in distant reservoirs. Some get enough energy to escape entirely. One clean gravitational slingshot and you are gone. Once escape happens, there is no return ticket. The sun will be just another star you pass by on your longer road. Interstellar travel sounds romantic until you remember the pace. A body like this drifts for ages through a vacuum barely warmer than absolute zero. It spins. It gathers tiny scars from stray dust. Its outermost layers get reworked slowly by cosmic rays that break bonds and rebuild them in different shapes. Nothing about that journey is dramatic. Everything about it is patient. The result is a surface that no longer looks like it did on the day it was thrown out, wrapped around a core that still remembers older conditions. The thick disk story helps tie the pieces together. Those stars tend to be older and sit higher above and below the thin disk. Their chemistry often carries patterns unlike ours. If 3i Atlas began there, it would explain why its gas looks non-local without breaking any rules. It might also explain why the subtle metal lines look off balance. When you grow rocks in a different interstellar kitchen, you get different flavors. The spectrum is our taste test at a distance. This is more than poetry. It is testable. Motions through space carry signatures, the way accents carry hints of where a person grew up. Track the speed and direction precisely, and you can rewind the path through the sun's neighborhood and ask which galactic populations the numbers match. It will never be a street address. It can be a neighborhood. Pair that kinematic hint with chemistry that points to deeper cold, and you now have two independent lines that converge on an origin older than Earth. Once you accept that frame, the visitor becomes a fossil. Not a dead one. A living fossil that still responds to sunlight with jets and tails, yet preserves a record from a time when our galaxy was young and noisy. A fossil lets you cheat time. You hold a piece of history without traveling back. If we can read the layers as the object wakes and cools, we can sketch how early disks sorted ices, how metal grains assembled, and how radiation in deep space reshaped surfaces over spans longer than human language has existed. The ejection chapter also pays forward into planetary defense. The same scattering that throws out interstellar wanderers shapes the belts and reservoirs that later feed near-Earth space. A cleaner map of how systems young and old throw debris helps us guess how often visitors will show up here and what sizes to expect. The tale of an elder from the thick disk is not a detour from safety. It is a lens that sharpens our picture of the whole traffic network. There is a final turn that brings the idea home. If a body can hold its structure across billions of years of cold and radiation, then its chemistry is not fragile nonsense. It is a durable message. December's window is our chance to record it before the voice fades with distance. We will not hear it again. Another wanderer will come someday with a different accent. For now we have this one. An elder that left its cradle before our oceans formed, crossing the dark with a library in its ice, arriving exactly when our instruments learned how to read. There is a moment in every great sky story when the curtain drops. For 3i Atlas, that moment is perihelion, the closest sweep to the sun, when the object is most alive and we are least able to watch. The glare floods our cameras. The elongation shrinks until even giant mirrors are staring into daylight. The comet does its most dramatic chemistry off stage while we stand in the lobby, checking our watches. The physics is cruel and simple. As the visitor dives inward, sunlight hammers the surface, turns buried ices into gas, and drives pressure through cracks that have slept for eons. Jets open, dust lifts, the coma swells, and the tail structures braid. All the signals we crave grow, stronger, precisely while the sun's bright field drowns them. From Earth's deck, the geometry lines up so the comet hugs the horizon before dawn and after sunset, never far enough from the star to give us dark sky plus good angles. This vanishing act is not a failure of telescopes. It is a lesson in perspective. We live on a world that rotates and orbits in lockstep with the very lamp we are trying to look past. There is a narrow wedge of sky near the sun that ground instruments cannot own for long. Coronagraphs can find sun-grazing comets that explode into gas, but they are blind to small dark nuclei that reflect little and hide in white glare. So the best scene plays behind the curtain, and patience becomes a scientific tool. While we wait, the comet faces a fork with two honest outcomes. Survival means a single, stitched nucleus holds together, vents fiercely, and emerges with fresh surfaces exposed and chemistry still legible. Fragmentation means thermal stress and spin pry, hit apart into a string of pieces, each with its own tiny coma and tail, a spectacle that photographs well, but scatters the record we hope to read. Neither path is rare. Both have precedence in our own cometary family. Then the stage manager called orbital mechanics moves the lights. Through November, Earth slides to a better line of sight. By early December, the comet steps out of the glare into the pre-dawn sky, where the air is steady and dark enough for deep exposures. The angle between sun, comet, and Earth softens. The night side stretches just enough to give spectrographs time to drink photons. Suddenly, the offstage exam turns into a press conference, and every instrument with a clear horizon wants a seat in the first row. The plan is a relay. Wide-field imagers fix positions night after night to tame the path, because outgassing acts like tiny thrusters and nudges predictions. Polarimeters read dust grain properties from the way light organizes after scattering. Infrared spectrographs measure warm dust and molecules that hide invisible light, giving us carbon dioxide to water ratios that say something clean about where this ice first condensed. Narrowband filters isolate nickel and any faint iron, so the metal puzzle tightens. Each technique is a different ear pressed to the same door. Weather, as always, is the unruly extra. That is why coordination matters as much as aperture. Southern and northern sites trade hours. Amateurs with good tracking keep photometry running between professional blocks, so we do not miss a flare that lasts a single dawn. Alert channels call audibles when brightness jumps, because a fresh vent can reveal chemistry that has not been cooked by earlier heating. December is short, and every clear hour is gold. There is a quiet human promise in this choreography. We cannot control the glare. We can control readiness. Observers clear schedules. Pipelines are tested so spectra are reduced before the night ends. Teams agree on priorities, so that if a fragment train appears, someone maps it while someone else chases gas lines, and nobody wastes the window arguing about credit. Curiosity is the fire. Logistics is the fuel. When the comet returns to view, it will not be the same object we last saw slipping toward the Sunday surfaces will be fresher. Vents will be louder or silent. The tail may be thicker, kinked, even multiple. If fragmentation happened, the map will include new points of light where one used to stand. Either way, the voice will be clearer for a few precious mornings. That is the December window. Not a miracle, just geometry finally on our side. So we accept the disappearing act as part of the plot. The most important chapter is not lost. It is delayed. We hold our questions, sharpen our tools, and meet the traveller at dawn when the curtain rises again. Then we listen hard, because what it says in December is the message we crossed a season to hear. When a stranger sweeps through your neighbourhood and does things your neighbours never do, rumour blooms. 3i Atlas arrived with odd chemistry, a crisp schedule, and a camera-friendly glow. It is natural to hear whispers that begin with "could it be?" Curiosity is healthy. The cure for runaway speculation is even healthier. We do not have to guess what evidence of technology would look like. We can name it, look for it, and check what we actually see. Start with motion. Technology leaves fingerprints when objects accelerate in ways gravity cannot explain. A controlled course change that does not match outgassing or solar pressure would be a flag. Oumuamua tempted people because it sped up a little without a visible coma. 3i Atlas is the opposite. It behaves like a comet should. It grows a coma and tail. Its tiny non-gravitational nudges track with jets that are obvious in images and spectra. Nothing steers, nothing hovers. The path curves exactly as sunlight, gas, and gravity say it should. Then, signals. A civilization that wants to be found can modulate radio or laser light with patterns that scream information. SETI groups listen across bands for that narrow, coherent fingerprint. They also look for repeating pulses or unusual polarization that natural plasmas seldom produce. 3i Atlas shows none of that. Its radio whisper is thermal noise from warm dust and faint molecular lines that every active comet sings. The light is sunlight reflected by small grains and glow from gases we can name. No beacons, no codes. Just chemistry and heat. Geometry offers a third test. Machines tend toward clean shapes and specular reflections that flash when sunlight hits at the right angle. Natural small bodies are lumpy and dusty. Their light curves wobble, but they do not mirror glint like polished panels. 3i Atlas shows the messy elegance of a venting nucleus. Brightness rises and falls with spin and jet activity. The coma's edge softens and thickens as dust flows. If a sleek object were hiding inside, the data would argue with itself. It does not. The simplest reading fits, an irregular, fragile nucleus wrapped in gas and grit. What about the chemistry that felt impossible at first glance? A carbon dioxide heavy coma, with water playing a softer part, nickel lines stronger than iron. Those ratios break our habits, not our physics. They point to a birthplace far colder than most of our comets, or to a disk with different elemental flavors, or to very old surface processing in interstellar space, where cosmic rays slowly edit the top layers. Each idea is a natural lever we can test as December spectra arrive. Exotic formation conditions are not exotic explanations. They are what you expect in a big galaxy. Psychology deserves a paragraph of its own, because it is the lens we all look through. Brains are brilliant at seeing agency. That talent kept your ancestors alive. When the sky delivers a one-in-a-decade visitor, your agency detector clicks on media, accelerates that click with headlines that turn nuance into drama. The way out is to keep two truths on the table at once. Weird exists. Weird does not imply intention. We can celebrate the first without leaping to the second. None of this means dismissing the long hunt for technology beyond Earth. It means keeping the bar where it belongs. Clear evidence would look like controlled thrust without a natural source, power output far beyond sunlight, materials with optical properties that defy geology, or unambiguous information in a signal. If we saw any of that, this episode would pivot in an instant, and you would hear the excitement in every observatory on Earth. We are not seeing that with 3i Atlas. We are seeing a rare chance to study a natural wanderer with alien chemistry in the best sense of that word, from somewhere else. There is also a generous middle ground that thrills scientists more than speculation ever could. Nature can be stranger than our catalogues and still be nature. Comet homes, once brightened by a factor of nearly 1 million in a single night. Shoemaker Levy 9, unravelled into pearls and plunged into Jupiter. Hale Bop, braided tails like a rope. 3i Atlas could add its own chapter. A layered nucleus might crack in December and spill fresh ices that rewrite the spectra. Multiple jets could spin up a tumbling motion we can track by the hour. Each surprise tightens physics rather than loosening it. So here is the invitation. Keep the sense of wonder turned all the way up. Keep the claims tied to measurable things. Ask of every headline, what would convince me if I were skeptical? Then look for that. When the answer is nothing short of a controlled maneuver or a clear signal, it becomes easy to enjoy what is actually in front of us. a messenger from a different nursery, writing its biography in sunlight and vapor. That is more than enough. The payoff for this discipline is not just pride in being careful. It is sharper eyes when a truly anomalous event does come along. If we practice now on a beautiful natural comet, we will be ready to recognize the difference later. For 3i Atlas, the difference is clear. Natural wonder, not engineered artifact. Familiar physics wrapped around unfamiliar chemistry. The sky is telling a story. We can hear every line without inventing a narrator. Here is a hard lesson learned the honest way. Early orbits wobble, probabilities change. Headlines do not like that. People do not either. Yet this is how real safety works in space and on Earth. You say what you know, you say what you do not know, and you promise when the next update will arrive. During the FA 22 week, agencies posted a small chance, then removed it as better data landed. That arc from maybe to know is not a flip-flop. It is the system breathing. The only way to build trust is to narrate that breath in real time. Start with the math behind the moving target. A new discovery gives you a short track across the sky. Many orbits can pass through those few dots. Plot them, and you get a smear of possibilities. Some threads cross Earth, most do not. A night later, the smear shrinks. 2 nights, and it shrinks again. The magic is not magic at all. It is geometry plus patience. If we explain that plainly, a change in risk feels like a forecast that sharpened, not a scare that fizzled. Now the language. Words like risk and hazard carry weight. Use them with care. A close approach inside the moon's distance can be routine. A tiny impact, chance years out, can be noise. A harmless flyby can still be thrilling sky theatre. The public needs verbs that fit the day. Approaching, tracked, refined, cleared. Those simple words keep emotions tethered to the real state of play. Avoid the fog of maybe bad. Replace it with a clear next step and a clock. We will update at dawn. We will post after the radar pass. Coordination is a second pillar. No single observatory owns the truth. Networks do. The international asteroid warning community exists to share tracks, compare fits, and publish the consensus that matters most when hours are tight. The craft is not only taking images, it is agreeing on what to say and when. During FA 22, teams traded measurements across longitudes, so the orbit never slept. That baton pass is the difference between rumour and rhythm. Tabletop drills sound dull until you watch one pay off. You run a live fire exercise with a candidate object, practice the public bulletins, test the alert lists, and write the after report while the stakes are low. Then, on a busy week, you lean on muscle memory. Who posts the update? Who pins the observation request to smaller telescopes? Who calls the radar team? If the answer is everyone and no one, hours vanish. If the answer is names and times, the curve of uncertainty shrinks on schedule, and a million people read a calm sentence instead of a shrill one. The media layer is where good intent can still bend into noise. Sensational frames are tempting. A mountain-sized rock buzzes Earth tonight smells like drama. The service frame works better and still draws eyes. A close pass tonight is harmless and visible to many regions. Here is how to look. Here is what we are measuring. Here is why it matters. Curiosity gets fed. Panic starves. Reporters want that path as much as scientists do when deadlines close in. Offer it early and often. There is a gentle script that helps when probabilities dance. Lead with certainties, distance, time. Size bracket, then describe the next measurement that will shrink the error bars. Name the instrument or the network. Put a timestamp on it. Remind people that early numbers move by design. Finally, mark the off-ramp. If the track tightens this way, risk will drop to 0. If it tightens that way, follow-up will escalate. That roadmap turns a floating maybe into a clear fork that anyone can follow. Social platforms compress nuance and amplify fear. You cannot fix that in a day. You can seed them with crisp visuals that carry truth at a glance. A simple diagram that shows Earth here, the object there, and a thick band of safe sky between them beats a paragraph. A small animation that shows the smear of orbits shrinking over 3 nights teaches the process in 5 seconds. When people can see the wobble narrow, they forgive the wobble. A final point about humility. Not every discovery will come with days of warning. The sunward corridor still hides small, fast movers until the last hours, though new infrared sentries will help. When a surprise arrives, say the word surprise. Admit what the geometry hid, then pivot straight to action steps. Track, verify, notify. If a late airburst ever happens again over a city, the difference between injury and grace will be the tone of the hour after the flash. Clear, calm, specific. The same habits that guide a good week guide a hard one. So we practice the truth under uncertainty now, while the Beckvow, sky is generous, and the visitors miss. We tune the message so the public learns what moving numbers really mean. We make sure school kids can repeat the cadence aloud. Discover, narrow, decide, share. When a real decision day comes years from now, that cadence will already live in memory. That is how you turn a noisy sky into a steady story, and how you keep wonder and safety in the same frame. The sky is not a show you only watch, it is a lab you can join. December's window for 3i Atlas will be short, precious, and perfect for a global relay where professionals and amateurs trade notes in real time. You do not need a mountaintop or a giant mirror. You need a plan, a steady mount, and the discipline to turn pretty pictures into numbers. When thousands of small observations stack up, they become a single, sharp measurement that no single telescope could have made alone. Start with the simplest gear that still respects the sky. A tripod and a camera that allows long exposures will do. Many phones now offer night modes that hold the shutter for a few seconds. A modest telephoto lens on a basic mirrorless body is better. A small backyard telescope with a tracking mount and a planetary camera is excellent. What matters most is steadiness and repeatability. Choose a pre-dawn site with a clear eastern horizon, away from porch lights and highway glare. Let your eyes adapt. Work in the hour before sunrise when the air is calm and the comet sits highest above the haze. Frame the field so you capture the comet and several known stars. Those stars are your rulers. Take sequences rather than one heroic exposure. 10 or 20 frames at shorter exposures often beat one long blur. Later you can average or stack them to pull out faint structure. Keep a simple log. Date in universal coordinated time spelled out, rough sky conditions, lens or telescope used, exposure length, and any filters. Those notes will make your data useful to people who never met you. But trust your care. There are 3 kinds of citizen measurements that punch far above their weight. Brightness over time is the first. Photometry sounds intimidating until you try it. You compare the comet's glow against nearby catalogue stars with known brightness, adjust for exposure, and write down a number. Repeat this on successive mornings, and a curve appears. A smooth rise suggests steady heating. A sudden jump signals a new vent or a fracture that exposed fresh ice. That one number, repeated by many eyes, lets professionals decide when to swing large spectrographs before the flare fades. Shape is the second. The coma edge, the tail length, and any kinks or striations change from day to day. Short sequences let you see if a jet is steady or pulsing as the nucleus rotates. Annotated sketches from binocular users still help, because the human eye excels at noticing asymmetries that an auto-processed image can smooth away. If your gear allows, polarizing filters and a simple rotation test can hint at dust grain size, a small touch that adds surprising value when shared widely. Position is the third. Accurate astrometry needs a tracking mount and software that maps your image to star catalogues. Many amateurs do this every night for asteroids. Doing it for a venting comet takes patience because the glow is fuzzy. The reward is real. Outgassing acts like a tiny thruster and nudges the path. A tight sequence of positions from many longitudes helps orbit fitters. Subtract that nudge and predict where the nucleus will be tomorrow dawn, not where an idealized point would be in a vacuum. Sharing is where your work becomes science. Post promptly to recognized community hubs where comet observations are pooled, using the standard formats they request. Keep your captions factual and your emotions generous. If you see a brightness jump, say so and include your method. If all you caught was a faint smear, that is still a data point that confirms a trend. When someone else reports a flare, try to confirm it at the next opportunity rather than debate it in the comments. The relay works when each runner moves the baton forward. Safety and sanity keep the joy intact. Pre-dawn work steals sleep. Go with a friend. Bring a headlamp with a red mode so you do not blind your night vision or your neighbors. Dress for cold ground and colder wind. Pack a thermos and the patience to let gear cool to ambient so lenses do not fog. If clouds arrive, log that too. A network that records null results is stronger than one that only sings on perfect nights. Most important, keep the dual mindset that makes citizen science powerful. Be a poet while you frame the shot, and an accountant when you write the number. Share the wonder in your voice and the rigor in your notes. Professionals will be sprinting through narrow instrument windows. Your light curves and positions will help them aim. In return, their spectra will decode the chemistry behind your glow. That is the partnership this moment invites. When 3i Atlas steps out of the glare, you can do more than look up, you can help listen. 10 minutes in the cold with a careful method is not a small thing. It is a brick in a bridge that spans backyard decks and billion-dollar observatories. Lay your brick, then warm your hands and watch as the global picture sharpens because you were there. Here is a prediction you can feel in your bones. 3i Atlas will not stay lonely for long. The same upgrades that let us catch this wanderer on the inbound leg are about to flip interstellar archaeology from once-a-decade luck into a steady stream. Rubin's cadence turns the sky into a time-lapse, where faint movers pop. Infrared sentries turn the sunward lane from darkness into daylight. Add smarter software and cross-network alerts, and the pipeline begins to hum. Rare becomes regular. Wonder does not fade, it multiplies. When that happens, the questions change. With one visitor, you argue about origins. With many, you begin to map neighborhoods. Carbon dioxide loud here, water loud there, nickel strong in one population, iron balanced in another. Patterns emerge that point to different kinds of stars and disks. Thin disk chemistry might cluster around one set of ratios. Thick disk elders might cluster around another. Suddenly, we are not staring at a single outlier. We are sketching the family tree of planetary kitchens across the Milky Way. The pace also forces new habits. Today, we scramble to assemble teams for a single window. Tomorrow, we run standing playbooks. One group locks orbits. One group runs first-pass spectra. One watches dust properties through polarization. One models outgassing to predict the small non-gravitational nudges that shift the track. Then we hand the baton to deeper instruments if a target looks especially strange or especially bright. The culture shifts from improvisation to choreography. That is how you stretch short dawns into complete stories. A richer sample set will rewrite models. Right now, our textbooks lean hard on comets raised in our own outer reservoirs. Interstellar data will tell us where that picture is provincial. Maybe many systems build carbon dioxide-dominated bodies far from their stars. Maybe some produce metal mixes we have never seen on local objects. Maybe spin states and cross strengths correlate with chemistry in ways that reveal how radiation in deep space sculpts surfaces over billions of years. Every new arrival is a control experiment that our own backyard cannot supply. The flood will also lower the barrier to a wild idea that stops sounding wild. A flyby probe that sprints to intercept an interstellar visitor on short notice. Until now, that sounded like a fantasy because the targets were too rare and the warning times too short. With more detections and earlier alerts, the math bends. You can build a small, fast chaser that sits ready and waits. When the next alien snowball appears, you light the stage and go. A close pass at tens of thousands of kilometers would turn spectra into mineralogy and coma models into resolved jets. If the approach is gentle enough, a tiny dust sampler becomes thinkable. Even without spacecraft, more visitors mean more chances for a different kind of capture. Interstellar meteors already rain through in microscopic sizes. Every so often, a sand grain-sized particle flares and leaves a spectrum in the atmosphere. Networks that watch the whole sky can triangulate the path and read the colors of the burn to recover composition. Stack enough of those, and you get ground truth to compare with the big comets. The point is not to chase hype. It is to harvest every scrap of information the galaxy throws at us. This new routine will sharpen planetary defense as a side effect. The same machinery that tracks exotic visitors also catches more local rocks early. The same software that models outgassing nudges improves orbit fits for hazardous objects that shed dust. The same global relay that shares comet alerts becomes the backbone for calm, rapid updates on close approaches. Curiosity and safety walk on the same road and carry each other's bags. Will familiarity dull the edge? Not if we tell the story well. The most powerful frame is not a drumbeat of crisis. It is the slow revelation that our solar system is porous. Material flows between stars. Worlds are not isolated projects. They trade ingredients through long corridors of time. When a new object appears, the line to the public is simple and true. We have another messenger. Here is what it carries. Here is what that says about where it was born. Here is how you can see it before dawn from your porch. The final turn is personal. The future of this field is not only bigger telescopes, it is a wider circle of hands. Teachers who turn a faint smear into a classroom of first spectra. Amateur networks that run photometry like a heartbeat monitor before work. Newsrooms that treat uncertainty as a feature to explain rather than a flaw to mock. If we build that culture now, the coming wave will not swamp us. It will lift us. So get used to the phrase interstellar visitor trending on a winter morning, not because the sky is suddenly busier, but because our eyes finally are. 3-Eye Atlas feels like a once-only gift. In a few years, it may feel like the start of a series. That is not a downgrade, it is an upgrade to our place in the galaxy. We are moving from spectators to surveyors, from coincidence to catalogue, from lucky to ready. Here is how the future bends when we choose preparation over panic. We write playbooks before the bell rings. We practice them when the stakes are low. Then when a real test arrives, the moves feel familiar. The September surge and the arrival of 3-Eye Atlas are rehearsals that teach 3 futures at once. The easy win, where detection is early and nudges are gentle. The stress test, where warning time is short and choices are tight. The long shot, where nature throws a size or speed that outstrips today's tools. If we face them now, we will not improvise later. The easy win looks like this. An object is found years out on the night side by Rubin, confirmed by infrared sentries, and tracked by radar when geometry allows. Orbit errors shrink to the width of a city street. A small kinetic impactor, designed from lessons learned by the double asteroid redirection test and mapped by Hera class forensics, launches on a routine rideshare. It arrives early, hits clean, and changes the path by a whisper that becomes a wide miss at Earth. Teams publish the numbers. Students watch the animation. 1 million people learn that disaster prevention can be quiet. The stress test looks different, but not impossible. Warning time is months, perhaps weeks. The target is in the 1 to 300 meter class, and the approach geometry is awkward. The menu shifts from elegance to urgency. One option is a faster kinetic strike delivered by a stripped-down chaser. Another is a gravity tractor that stations a spacecraft near the body and tugs for as long as the clock permits. A third is a standoff device that vaporizes surface material to create thrust without shattering the target. None of these moves are magic. All are better with even a little more time. That is why cadence and sunward coverage are not luxuries. They are the difference between a nudge and a gamble. The long shot is honest too. A truly large, long-period comet discovered late carries energy that current systems cannot erase on short notice. The plan shifts to civil defense. Evacuation maps for coasts if an ocean strike is possible. Glass hardening and shelter guidance inland if an airburst is likely. Power grid precautions. Hospital surge plans. Clear public briefings that trade theatrical language for specifics. Time, distance, direction. We practice those messages now on safe flybys so they do not feel like a new language on a hard day. Governance sits under every scenario. Who decides when a deflection moves from study to action? Which nation leads if the risk corridor crosses many borders? How do we audit models and share data fast enough that consent is informed and global? The bones of this exist already in the international asteroid warning community and in space agency partnerships. But bones need muscle. Regular exercises with public after reports. Open simulation tools that any university can run. Clear thresholds that trigger each stage of response, from attention to alert to action. When lines are agreed ahead of time, politics inflames less, and science speaks more. Multiple simultaneous threats deserve their own line on the checklist. September hinted at it. Imagine 2 city killer candidates inbound from different longitudes within the same season. Do we have enough tracking time, enough radar windows, enough mission planners to run both threads without starving either? The answer can be yes, if we invest in redundancy and train teams to divide cleanly. No single observatory owns safety. Networks do. That applies to people as much as to telescopes. Equity matters more than it sounds in a story about rocks and orbits. Coasts with fewer resources hug the same seas as wealthy ports. Inland towns with old windows are cut by the same glass as brand new towers. A good playbook shares detection results in every language and pushes practical steps through schools and local media long before any crisis. Science earns trust when it remembers the most vulnerable first. Culture is part of preparation. The more often the public watches a safe, close pass explained well, the less oxygen there is for panic when a real threat appears. Replace dread with literacy. Replace rumor with diagrams that show Earth here and the object there with kilometers and dates spelled out. The same storytelling that turns 3i Atlas into shared wonder can turn a deflection mission into a civics class where the homework is simple: know the cadence, discover, narrow, decide, share. Technology will keep sprinting ahead, but logistics is where many good plans trip. So we make the boring parts beautiful. Checklists that name people, not just roles. Data pipelines that reduce spectra before sunrise. Alert templates that fit in one screen and survive screenshots without losing meaning. Dry runs where teachers and amateur networks receive the same bulletins as agencies and practice turning them into useful local posts. When a system works under routine pressure, it will hold under real pressure. The final truth is steadying. Planetary defense is not a cliff edge we back away from in one leap. It is a staircase with many small steps, bigger eyes, earlier alerts, smoother handoffs, smarter nudges, clearer words. If we keep climbing, the night a mountain-sized rock writes its name on our calendar will be the night a calm sentence appears in every feed. We see it. We know it. We have time. Here is the plan and here is the clock. That is what a planet that plans sounds like. Stand under a clear sky, and you can feel two truths at once. We are tiny. We are not powerless. The September surge and the arrival of 3i Atlas are a lesson in how awe can become agency. This is not just about rocks and comets. It is about how a species learns to cooperate at planetary scale. The same muscles that let us track a visitor from another star are the ones we need for climate, for pandemics, for anything that does not care about borders. The sky is generous. It gives us a practice field where the stakes are manageable and the rewards are obvious. Start with literacy. Once you know why tails point away from the sun and why orbits shrink from smear to line with each night of data, you stop treating space as superstition. You begin to ask sharper questions everywhere. What is the next measurement? Who is sharing it? When will we know more? That habit travels. It makes you better at reading a weather forecast, a medical study, a budget. A planet that reads the sky with care is a planet that reads other complex systems with care, then trust. The relay that passes a comet alert from a small dome in the Andes to a backyard in Arizona to a spectrograph in Hawaii is trust in motion. Cameras speak the same formats. People speak the same cadence. Discover, narrow, decide, share. That rhythm is not owned by astronomy. It works for wildfire maps and river flood warnings and vaccine rollouts. Each time we practice it on a beautiful object at dawn, we make it easier to keep our heads when the day is hard. There is a civic layer that hides in plain sight. When a safe close pass makes news and the message lands cleanly, millions catch a glimpse of institutions doing something right together. Space agencies and universities and school clubs and amateur observers moving as one without shouting. That is oxygen for public patience. The view that science and government can be competent partners is not a luxury. It is the floor under every long project that makes tomorrow better than today. Art and meaning ride along with the measurements. Every image of a green coma over a city skyline is a reminder that we live inside a story that started before our oceans formed. That does not trivialize daily work. It honors it. When a night shift nurse walks out of a hospital and sees a faint tail in the east, the two worlds touch. Healing one body and learning one comet are both acts of care. Wonder is not an escape from responsibility. It is a reason to keep going when the tasks are heavy. Equity belongs in the sky story too. A comet does not care about passport stamps. The wave from an ocean strike does not either. If detection networks and public bulletins only serve those with the newest phones and the best schools, we fail at the one job the cosmos handed us, which is to keep everyone on the boat alive. Translation, radio, community teachers, local newsrooms, all are instruments as vital as a mirror polished to a fraction of a human hair. The playbook is only real when the most remote village can use it at 4 a.m. There is a quiet economic argument that ties these threads together. Prevention is cheaper than repair. A survey that moves discoveries from days to weeks of warning is a bargain. A mission that nudges a rock by a few millimeters per second, years out, is a bargain. The same logic builds levees before floods and upgrades power lines before storms. The return on investment is paid in schools that do not close and towns that do not rebuild. Space teaches that clearly because the geometry leaves no room for spin. Finally, there is identity. For centuries, humans drew circles that kept most people out. The map kept shrinking until a camera on the moon showed all of us inside the same small blue halo. 3i Atlas adds one more piece to that portrait. We are not only a people of one planet. We are a people in a galaxy that trades material across the dark. To act like citizens in that setting is to keep our tools sharp and our arguments honest. It is to admit uncertainty out loud and to cheer when a scare becomes a non-vent because the numbers move the right way. In a few weeks, as dawn brings the comet back to view, you will have a chance to feel this directly. Point a lens, take a reading, send it where it helps. You will be part of a network that stretches from kitchen tables to mountaintops, all focused on a single, ancient traveler that will never return. That is what cosmic citizenship looks like. Not slogans, not panic, practice, patience, shared work, or that points somewhere useful. The sky will keep handing us chances to be that kind of species. The rest is on us. Before dawn, the horizon is a thin electric line, and the air holds its breath. This is where our story lands, not in a control room, not in a headline, but in that quiet place, where you can hear frost whisper off a tripod leg and watch the east pale by degrees. In the next window, 3i Atlas will step out of glare and into this silence. We will have minutes, then hours, then a handful of mornings to ask the right questions fast, in the right order, with the right tools, so the answers add up to more than a pretty picture. What are those questions? First, survival or fracture. A single nucleus that held together through the furnace tells one tale. A string of shards tells another. Either way, we map every point of light, measure separations night to night, and let dynamics speak. Second, chemistry under stress. Do the carbon dioxide to water ratios stay extreme or slide toward familiar as deeper layers vent? Do nickel lines stay loud while iron stays shy? Spectra across successive dawns will turn that maybe into a map you can argue from, not around. Third, structure in motion. Photometry will show if brightness breathes on a clean rotational rhythm or coughs through irregular outbursts that betray crusts popping and vents moving. Polarimetry will say whether the dust is fluffy like fresh snow or compact like weathered sand, and how that changes as the nucleus reveals new skin. Fourth, the tiny pushes that matter. Outgassing is thrust. Thrust is path. A tight chain of positions from many longitudes will let orbit fitters subtract the jet effect and pin down where the nucleus will be tomorrow, not where a point in a textbook would be. Behind those questions is choreography. Wide-field images set the frame. Infrared instruments read the warm dust and the molecules that hide from visible light. Narrow band filters split nickel from iron and watch for faint metals that only appear when heating reaches new depths. Teams trade the baton across oceans, so the comet is never alone in the sky. Amateurs run light curves between professional blocks. Pipelines reduce spectra before breakfast. Updates go out in clear, steady language that tells everyone what changed and what did not, and when the next look begins, you do not need to hold all of that in your hands to belong to this morning. Take the simplest role that still respects the sky. A careful photograph with reference stars and an honest note about haze, a brightness estimate repeated on 2 consecutive dawns, a short log that says when the tail kinked and which way. Add your brick to the bridge. If you cannot go outside, follow the relay and notice the cadence. Discover, narrow, decide, share. That rhythm is the whole point of this series, and the skill that will serve us for threats and wonders that are not comets. There is a quieter reason to meet this traveller at first light. It puts you in the same frame as everyone else who is watching. A student on a rooftop in Lima, a farmer in a field outside Warsaw, a nurse stepping out after a night shift in Bangkok, a spectrograph operator on a mountain where the wind tastes of ice, all looking toward the same pale wedge of sky where a piece of another star's nursery is drawing breath in sunlight for the first time in ages. That is citizenship of a kind that no passport issues and no argument can cheapen. If the numbers slide toward familiar, celebrate. It means nature is consistent even when it looks strange at first glance. If the numbers stay alien in the best sense of that word, celebrate differently. It means the galaxy's pantry carries recipes our neighborhood never tried, and we just tasted one. Either way, the win is the habit we practice together, turning awe into method, without grinding the awe away. Soon the object will fade, carrying its green whisper past the edge of our maps. Another will come. We will be ready earlier, listen longer, argue better, and invite more people into the circle. That is how a planet grows up without losing its sense of wonder. This is where we leave the story for now. At the edge of dawn, with instruments warm, eyes open, and the next frame already. Loading. If this work moved you, bring someone with you to the morning watch. The sky is generous. The rest is on us.